When you build software by simply writing code and hoping the pieces fit, you eventually hit a wall. Teams spend weeks trying to force these pieces together, and integrations break down. Moving past that requires shifting to a structured system. The International Software Architecture Qualification Board provides a global standard to solve this exactly. Their foundation-level methodology offers a clear, repeatable process for designing software that actually scales. To get the most out of this process, you should already have some practical experience with a higher-level programming language, and ideally a specific system or project in mind that you want to improve. We are going to apply a rigorous engineering discipline to your project. By following specific steps, we systematically reduce technical complexity and build a solution that works predictably. Step 1 is defining the boundaries of your system. We gather all stakeholder requests and sort them. First, we capture functional requirements, what the system actually has to do. Next, we determine quality requirements, how secure, fast, or maintainable the system needs to be. Then we map out the constraints. These are the fixed realities of your project. They might be organizational limits, like a strict budget, or technological limits, like mandated hardware and programming languages. You have to watch out for implicit assumptions here. If everyone assumes the app will be hosted in the cloud, write it down anyway. Leaving unsaid details out of your documentation leads to severe misalignments later on. Once you explicitly document these requirements and constraints, you have an objective foundation. Every technical decision you make from here on out will be measured against this list. Step 2 is decomposition. You cannot build or maintain a monolithic block of complex logic. You must break it down into smaller, self-contained modules or building blocks. To make this work, we apply the principle of loose coupling. You want to design these building blocks so that they rely on each other as little as possible. At the same time, you need high cohesion. That means grouping related functions tightly within the exact same block, so a single module handles a single specific job. This Java code snippet shows how we enforce these boundaries using abstraction. The animal interface dictates what a component can do, like eat and move. The horse class implements those commands internally. The rest of the software interacts only with the clean interface, hiding the complex, messy implementation details completely out of sight. By structuring your system with high cohesion and loose coupling, you isolate failures. An update or error in one module is prevented from triggering cascading failures across the entire application. Even with perfectly separated modules, you still face a major risk: independent developers solving the exact same technical problem in entirely different ways. This creates fragmented code that is nearly impossible to maintain. Step 3 solves this by defining cross-cutting concepts. These are global rules that apply across all modules. Think of database persistence, security protocols, communication methods, and graphical user interface standards. You must lock down these global rules early in the design phase. They aren't details you can figure out on the fly. Setting these standards early forces everyone onto the same page. It ensures the whole system communicates in one consistent language, regardless of who writes the underlying code. Step 4 is documentation. A brilliant architecture doesn't mean anything if you can't hand it over to developers to build or explain it to managers to fund. We translate the design into standardized formats. First is the building block view. This maps out the static structure of the system, showing the distinct modules and how they connect to one another. Next is the runtime view. This illustrates the actual flow of data, showing how information sequences through the different nodes while the program is actively executing. Third is the deployment view. This maps your virtual software artifacts directly onto the physical hardware or cloud environments where they will actually live. Finally, we use architecture decision records, or ADRs. While diagrams show what you built, ADRs document exactly why you chose one structural path over another. Together, these views and records take your subjective design ideas and lock them into an objective, defensible blueprint. In Step 5, we test the blueprint before a single line of code is written. You take your completed architectural views and stack them up against the constraints we gathered back in Step 1. You explicitly check the design against your metrics. Will this layout handle the required user load? Does the data flow meet the mandated security thresholds? Will the deployment nodes guarantee uptime? This is the moment to identify structural risks. It costs almost nothing to fix a bad connection on a diagram, but it is deeply expensive to tear apart a fully coded system. Rigorous evaluation acts as your final gate. It validates that your design and measurement criteria align with the business goals you were hired to solve. By following these steps, you transform a vague set of project ideas into a highly structured package. You now hold a baseline of requirements, standardized visual views, strict cross-cutting concepts, and clear decision records. But the process doesn't end at handoff. Architecture is inherently iterative. As developers begin implementation, they will find edge cases. You will need to take their feedback and refine the blueprint. To formally master this methodology and prove your ability to guide complex builds, review the official iSAQB Foundation-Level Certification Curriculum. Successful software architecture is a continuous, disciplined practice of aligning technical execution with fundamental stakeholder needs.